From our previous lecture video, we saw how the chi-square test statistic can only take on positive numbers. Thus, it follows a different distribution called, you might have guessed it, the chi-square distribution. And we can see on our visualization that all of these chi-square distributions that you see here never go below 0. What you may notice is the degrees of freedom, like we saw with t, drastically is changing the shape of your distribution. For a chi-square distribution, it has degrees of freedom just like t, but in this case, instead of the number of observations minus 1, we look at the number of categories minus 1. That's going to determine the number of degrees of freedom that we have. How many categories are we estimating? Minus 1. We can see visually that degrees of freedom of 1 looks very different than degrees of freedom of 10. Degrees of freedom of 2 looks very different from degrees of freedom of 3. So the amount of degrees of freedom you have drastically affects the shape. Let's see why that is. What we need to think about is what would cause our chi-square test statistic to get large. Well, one of them is analyzing more categories simultaneously. Right? We saw in our previous example, we were looking at high, middle, and low income families. Essentially what happened is we each had a quantity Q1 plus Q2 plus Q3, and these just represent values. Well, what if we added other groups, like very high income and very low? I'll just write V low. Well, then we would be adding more quantities. The fact that we're just adding more numbers together is going to result, and it's more likely for us to get a higher test statistic. The more things we add together, the more likely it is to get a bigger number. So because of that, this chi-square distribution is taking that into account. It's saying, hey, more groups means it's more likely to get a large test statistic. The other thing that we have to take into account, maybe more importantly, is when we compare our observed versus expected. When we look at our observed versus expected frequencies, the more different those are from each other is going to result in a larger test statistic, right? We're looking at the quantity observed minus expected squared. So whether your observed is much lower or much higher, so differ could be higher or it could be lower. Whether it's much smaller than what we expect or much larger than what we expect, we're squaring those differences. That will result in a larger test statistic. The more what we observe differs from what we expect. So because of that, the larger test statistic we have, the more likely it is that the population proportions differ from what's hypothesized. Right? If what we observed is different from what we expected, those original population proportions may not be accurate. Right? But if what we observed equaled what we expected, so imagine we got the same value, well then we look at the quantity observed minus expected squared. If what we observed is exactly what we expected, this kind of value right here, well that would come out to be 0. If you got exactly what you expected. So the larger difference you have, the more likely is it that what you expected is probably not true. Thus, a large test statistic will give us evidence to reject the null hypothesis. The larger test statistic we have, the more evidence we have against the null. So keep in mind, a big test statistic, therefore, will support HA and go against your null. So when we find our p-values for a hypothesis test, and we're looking at this chi-square distribution, all right, chi-squared with a certain amount of degrees of freedom, what we're going to do is look at our test statistic, all right, TS, and we're going to find all the area greater than, because that will support the HA. The bigger test statistic we have, the more evidence we have against our null and for our alternative. Thus, to coincide with our HA, we look for greater than. So this area right here will be our p-value. And that will be true for all of these chi-squared goodness of fit tests that we do. Let's find our p-value from this problem. Here we have our chi-squared distribution calculator. And notice it doesn't show the shape of your distribution yet because we don't know the degrees of freedom. For our problem, we had high, middle, and low income families. So our groups was 3 minus 1. We should have 2 degrees of freedom. Our test statistic, if we remember, was 15.17. And we'll hit enter. Therefore, our p-value for this problem is giving us all that shaded area being greater than 15.17. There's not a lot under there. And that's 0.00051, or a percentage of 0.051%. That would be our p-value for this test.